All right, so we're in Algebra 1. We are on lesson 9-2, multiplying monomials. Today's date is Thursday, March 5th, 2015. Before I even ask for someone to read the objective, I want to ask, what is a monomial? Does anyone know what this word mono or mono, depending on where you live, means? Oh, a lot of people know. Yeah, Eamon? One. So if we can all underline the word, oh yeah, thank you. If we can all underline the word M-O-N-O, mono, and write a 1 up above it. So that means one term, and then meal, I guess, means number. So if I'm saying a monomial, I just mean one term. So let me give you an example of what a monomial looks like. If we look down here, this is a monomial. This is a monomial. This is a monomial. This is not. This is a binomial. There are two. Bi, like a bicycle, has 2 tires, a unicycle. Question, Charles?
Wouldn't all that be a polynomial?
Yes, so I can call anything a polynomial. I can write the number 2 and say, yeah, that 2 is a polynomial. So polynomial is a very broad category, so you're correct, yes. So this is a monomial times a monomial times a binomial, and I could even give you a monomial times a trinomial. Yeah, what?
Is a monomial like a term by itself?
Yeah, just a term by itself. All right, so, and yeah, I was going to say other stuff, but that's good. Okay, so, objective. Who's got it? Eamon, no, I'll take your card.
Multiply a polynomial with one term with polynomials with multiple terms.
There it is. So, multiply a monomial by polynomials, in other words. All right, so there is a big difference between adding and multiplying. So all of 9-1 was adding and subtracting, and now we're going to be multiplying. So that giant rule that I said, your power will never change, your exponent will never change whenever you're adding. Now we're going to multiply, and we're allowed to change the power. So if I do 2 plus 2 plus 2 with a quiet raised hand, there are 2 ways of writing that. I can obviously get the answer, which, what, Charles?
Well, the answer would be 6.
6.
Same as 2 times 3.
That's the main thing, yeah. Which is really 3 of those 2. So 3 times 2. So this 3 is kind of important. It counts how many times we're adding the same number. And what do we call the number out front? When I'm talking about a polynomial or a monomial, any sort of thing with a variable, let's pretend that 2 is an x. What do I call that number out front? Kira?
Constant.
You're correct that it's a constant, but when it's attached to a variable, it has an even more specific name. Do you remember what that was called?
Coefficient.
Coefficient, yes. So everyone write down the coefficient. Do you already have the next one, Charles, or is there a question? Oh yeah, question, go for it.
Shouldn't the 2 be out front? Well, I guess it doesn't.
Yeah, it's the same thing, you're right. So the coefficient is going to count how many times I'm adding the same number or the same variable. So I'm going to also add to this number slash variable. All right, so therefore, if I'm adding x squared plus x squared plus x squared, how many times have we added x squared, and what is my final answer here? What?
X to the power of 50.
Not quite. So I still, just like these 2's, I grouped up these 2's and just put it there. So I'm going to group up these x squares and put it there, and then the coefficient is going to tell me how many times I've added that same variable in this case.
3 times x to the power of 50.
There it is, 3x squared. So again, this is what we did yesterday. If I have x squared plus x squared plus x squared, we said, okay, I have 1x squared, 1x squared, 1x squared. I add these coefficients, and I say, yes, the answer is 3. If I had 2x squared, 2x squared, 2x squared, 2 plus 2 plus 2 would be 8, and I write 8x squared. I'm really just adding the coefficients. Yes, Charles. Ready for the next one? We'll give it to someone that has a card. 2 times 2 times 2. We just did a giant unit on exponentials. You do have a card. Go for it, Charles.
It would be 2 to the 2 cubed.
2 cubed, yeah. 2 to the power of 3. And 2 to the power of 3 is what, Charles?
It is
8. Perfect. Thank you. So, and again, if I'm just counting, I say, okay, I have 1, 2, 3 of those 2. So 3. 3 is the thing that's counting how many times I multiplied by the same number. That 3. What is that 3? It is a, with the acquirer's hand, who has their card? Only 2 people know the answer here. What do I call this thing whenever it's up here? It has a specific name. More people have it. Oh, yes, Ugo, you have your card raised. Yeah, the exponent. Thank you, Ugo. Okay, so, and again, same number / variable. So, this one is a little bit tricky, but I'm thinking that we can do it. Really, what I'm saying here is I have 2 x's. Right here, this is saying x times x. This x squared is also telling me I have x times x. This x squared is also telling me I have x times x. That's what the definition means. These exponents right here are saying I have counted 2 of these x's being multiplied together. Read the definition again. Make sure that this matches with this. X times x is x squared. I'm counting 2 x's that are being multiplied. How many times have I multiplied? 2. Okay, well then, if I multiply all these together, I'm counting how many times I'm multiplying x. 1, 2, 3, 4, 5, 6. I'm really saying x squared times x squared times x squared is what? Who has a card? Emma.
6.
Ooh, really, really close. So I agree that x's are variable, but it's going to be the exponent is going to count how many times we multiplied. So we've multiplied how many times? How many times did we multiply the x? X times x times x times x.
6.
6. So that 6 should go out front with the coefficient or up above with the exponent.
With exponent.
Done, right there. X to the power of 6. Question, Charles.
Can you also add the exponents?
You could also add the exponents. Yeah, we have our rules of exponents that say if I have anything with the same base, these are all the same base down here, they're all x, and I'm multiplying, all you have to do is add 2 plus 2 plus 2, that's 6. And I'm glad that you see that, and I'm hoping that everyone else sees that as well. This is relating back to like 2 or 3 units ago now when we did our rules of exponents. I think it was only 2 units ago. Okay. And if you have room, I should have left room. Can we write that down? Because I haven't added that to my notes ever before, but I think it's really important to say this x to the power of 6 is really x to the 2 plus 2 plus 2. We really added those 2's. And Charles, he stole my thunder. I was about to have the giant reveal down here, which is, I'm going to call it Charles's rule now for this unit. Charles's rule says that if I have the same base and I have 2 different, they might be the same, but I have an n and an m there, what do I do when I have the same base and I'm multiplying them? What do I do with their powers? Do you have your card, Jade? No. Who has their card? Yes, Ulysses.
Don't you add them?
You do, so what am I going to write here?
X plus to the power of n plus n.
There it is. Everyone write it down. X to the power of n plus m. And then I'm going to do a little squiggly to say that was something else. Question, Asha.
So, say we had x to the power of 1 times x to the power of 2, if you just add 1 and 2, it'd be x to the power of 3.
100%, yes. Are you ready for the next one, Charles? That's pretty good. All right, so I'm going to extend this rule a little bit and add some coefficients in here. So if I hide the a and the b, it's the same thing as the previous line. So obviously I'm going to have some sort of x to the power of n plus m, but I'm adding in some coefficients now. Anyone have an idea of what this formula is going to show us? I'll give you a hint. You're going to rewrite this. Something's going to be out front. What's going to be out front? I'm going to have to probably call. I want to try to get all the cards in from the get-go. All right, how's he? AX. So you can rewrite this part right now, right? X to the power of n plus m is going to be the same thing.
So it's gonna be x plus n, then the a and the b are gonna be together.
The a and the b are going to be together? Yeah, exactly. So a times b like that out front, and times that x to the power of n plus n. There it is. I'll take a card to just turn it in. So what Hazy is telling us here is the a and the b, we just multiply whatever those numbers are. This is a 2 and this is a 3. 2 times 3, so the coefficient is now going to be 6. Multiply the coefficients, add the exponents. I'm about to write that down again down below. All right. So we have Charles's rule and we have Hazy's rule. All right, so let's turn this rule that I just wrote, let's write Hazy's rule in words. How do we say that? I just said it, you just need to regurgitate it now. And there's still at least 2 cards. No, I think there might just be 1 card. All right. So Larissa, I think it is you now. So we're multiplying these. This is a polynomial and this is a polynomial. So we're multiplying these polynomials. What are we going to do with the coefficients? What operation did we do with these a and b? Be careful here. What operation was this right here? Yep. So. Oh yeah. So, like the bottom one, like a and b, these bottom ones, or. Oh, okay. So these are technically coefficients, and then exponents are these ones up here. All right. So say it again. What do we do with the coefficients? Everyone write it down with us. Multiply. And then what do we do with the exponents? These exponents up here. There it is. So we have Hazy's algebraic rule, and we have Hazy's rule written in words. Use whichever one you like. If you think that one's easier to memorize, use it. If you just like saying multiply coefficients, add the exponents, use that one. Use whatever tool you like. Question, Kira.
Could you say combine the coefficients?
Yeah, so combine is too general of a word. Do you combine them by subtracting them? Do you combine them by dividing them? If combine in your language means it's always going to be adding or something, then yeah, you can use your own language. Like, these notes are for you guys. Make them make sense. All right, so we have 3 examples. Let's do the first one. I think everyone's card is in, right? Can you guys check your neighbors? Did I miss anyone? I have everyone. Charles, you've been waiting so patiently. Go for it.
So 3x to the power of 1 and 2x to the power of 2.
Oh, I like how you said that. Everyone, can you write that down too? Charles said that this is really 3x to the power of 1. If I don't see a power, assume it's 1. And then keep going, Charles.
So then it would be 6x to the power of 2.
Done. Box it. It's that easy. Someone explain his work. A question?
So if it's a negative coefficient, would we subtract the exponent?
Exactly, yeah. A negative 1 and a 2 adds to just 1. Someone explain how we got 6. Someone explain how we add to the power of 3. Kira.
Well, 3 and 2 are the same as a and b were in the example, so he just multiplied those.
Okay.
And then x and x are the same coefficient or variable, so you can add 1 and 2.
Cool, thank you. All right, let's try another one. Ooh, this is going to be a little bit harder. We're going to have to, what's that D word? Can you guys all shout out that D word that means this into this into this? It's called distribute. Okay. So, I'm going to have to do 2 of these now. All right, who is our quiet raised hand that I'm going to call on? Who can distribute both of these? Yeah, Ulysses.
Would it be like distribute the negative 1k and 5k would be 20k to the second?
20k to the second like that?
Yeah.
Okay, yeah. There's 2 tiny mistakes. I'll let you see if you can find them first. So I'll give you a hint here. A negative times a positive
Or negative 20.
is negative 20. Perfect. And then there's something that we have to do also with the power. So if I'm adding powers, 3 plus what? And what should my answer be?
4.
4. Okay, yes. So I'm going to come back up here and say this is negative 20k to the power of 4. Everyone is okay with this? We're good? And I'm also going to come back here and add some notes. So this is k to the power of 1. If you don't see a power, assume it's 1. You don't have to write it every single time. I'm doing it to be very clear in these notes. All right. And then who's going to do our second term? Yeah, what?
So you'd still distribute negative 4k to the power of 1 into 2, and negative 4k times 2 would be negative 8k, right?
Negative 8k. There it is, yeah, and that's correct. There's our final answer. We'll box it. Yeah, again, if you don't have any k's to multiply by, k to the power of 1 plus nothing is still k to the power of 1. So over here we have k to the power of 1. Technically, if you want to be like really pedantic, going overboard, you can really say that this 2 right here is 2k to the power of 0. Because anything to the power of 0, and everyone's going to shout this one out, anything to the power of 0 is 1. So 2 times 1 is 2. So what I'm really doing here is I'm adding k to the power of 1 plus k to the power of 0, or I'm adding 0 and 1 rather. 0 plus 1 is still 1. So that's another way of kind of interpreting this problem. Question, Kira.
Well, how are you done like 20k to the 4th? Couldn't you combine 20k and 8k to get
Negative 28.
yeah, like couldn't you just
Okay, that's a great question. I want someone else to answer that. Can't we just combine those terms?
wait? Is it because you're subtracting?
Possibly. It depends on what your interpretation is. Yes, we are subtracting, and because we're subtracting, what does that mean?
That you can't go on because the exponents are different.
That's the analysis, yeah. Our exponents are different, and because we're adding and subtracting now, we're going back to yesterday's lesson 9-1. Whenever we're adding and subtracting, we can only add and subtract like terms, which means the same variable, the same letter here, and the same exponent. So if these are different exponents, I cannot combine like terms. That's as far as I can get. Let's try another one. Our final problem. I need 2 volunteers, one to do the first distribution, one to do the second distribution. Jade, you're up first.
You distribute negative 8 v to the second into 4v to the second. You get negative 34 v to the 4th power.
V to the 4th power. There's a tiny mistake. I'll let you see if you can catch it. It's just a multiplication mistake. If you had a multiplication table, you would not make this mistake, in other words. 32, good catch. I love it when students catch their own mistakes. It's much more powerful. So v to the 4. Thank you, Jade. And finally, I'm going to distribute our last time for the entire lesson. Ugo. Is it a positive or a negative 48v? I guess a positive 48v to the power of 3. Box it. Question, Larissa.
You said that, like up on when we were chart up top here. You
Yes.
said that the bases had to be the same to be able to add, but we didn't do that. So is that like because we're distributing?
So we have to be careful what we mean when we say the word base. When I say base, I mean the thing that's underneath the exponent. So 4 is technically not underneath the exponent. 6 is not underneath the exponent. It's just the v. So when I have a v to the power of 2, a v to the power of 2, a v to the power of 1, all of these are the same base as all of these. Yeah, that's a great question. Yeah, Charles, question.
So for the negative 8v to the power of 2,
Yes.
when you combine that with the 4v, wouldn't it just simplify the 1? Or
Oh, because you see a negative and a 2,
Yeah.
is that what you're seeing? Oh yeah, so if this right here is a negative 2, then yes, it combines to 0. But yeah, you just have to look at the power independent. Alright, so give me a fist of 5 for our objective today. How well can you multiply a monomial by polynomials? I'm seeing a 4, a 4, a 5, a 4, a 5, a 5, a 4, a 5, a 4, a 4, and a 4. Alright. I'm rounding down to the nearest whole number. So if you give me a half, I'm going to give you, like if you give me 4.5, I'm going to say 4. Good job, guys.